Have you ever looked at a confusing enzyme graph and wondered how scientists actually read it? Let's fix that. Hi everyone, today we're going to look at the Lineweaver Burk plot, a simple but powerful way scientists study how enzymes work. You might have seen enzyme graphs before. They curve upward and then level off. That's called the Michaelis-Menten curve. It shows how reaction speed changes with substrate concentration. It's useful, but as the curve flattens out, it's hard to read exact numbers, like how fast the enzyme can go or how strongly it binds its substrate. That's where the Lineweaver-Burk plot comes in. It takes that curvy graph and straightens it out, making everything way easier to interpret. Okay, but what is an enzyme? How does this work? Let's break that down. An enzyme is a protein that acts as a catalyst, so it helps speed up chemical reactions without being consumed in the process. All enzymes need to bind to a substrate's active site to become active. So you can picture the more enzymes and substrates you have, the more binding of the two, and the quicker the reaction will happen. In a Michaelis-Menten graph, as you add more substrate, the reaction speeds up, but only to a certain point. Eventually, the enzyme is working as fast as it can. That's called the Vmax, or maximum velocity. The curve of the graph levels off, which makes it tough to tell exactly where Vmax is, and even harder to find Km, which tells us how well the enzyme binds its substrate. So scientists needed a clearer way to get these numbers, something more precise than guessing from a flat curve. Whoa, so how does this work? To fix this, scientists used a little math magic to replot the data using reciprocals. Instead of velocity in v, they plotted 1 over v, so it's 1 over velocity. And instead of substrate concentration, which is S in brackets, they plot 1 over substrate concentration, which is 1 over S in brackets. When you do this, the curved Michaelis-Menten line straightens out, and straight lines are much easier to work with. But here's the cool part. Where the line crosses the y-axis, it gives us 1 over Vmax, and where it crosses the x-axis, it gives us negative 1 over Km. So this means you can calculate both Km and Vmax directly, so no guessing, no estimating, just clear numbers from the line. Let's look at an example. Take lactase, the enzyme that helps break down lactose, which is the sugar found in milk. If you plot lactase activity using the Michaelis-Menten curve, it's hard to tell exactly where Vmax and Km are. The curve flattens and the numbers are fuzzy. But if you use a Lineweaver-Burk plot, you get a straight line that clearly shows the intercepts for 1 over Vmax and negative 1 over Km. Now, scientists can easily compare lactase to other enzymes to see how conditions like temperature or pH affect its values, all using one simple line. Here's another way to think about it. Imagine you take a photo that's a bit blurry. You can tell what's there, kind of, but the details are fuzzy. Then you adjust the focus and suddenly everything becomes sharp and clear. You can finally see where things really are. That's what the Lineweaver-Burk plot does for the enzyme data. The Michaelis-Menten curve gives you the overall picture, but it's a little hard to read. By transforming it into a straight line, the Lineweaver-Burk plot sharpens the focus, so Vmax and Km stand out clearly. To sum it up, the Michaelis-Menten curve is great for showing how enzymes behave, but the Lineweaver-Burk plot makes it easier to measure what matters, which are Km and Vmax. It's like taking a complicated curve and making it simple, so scientists can clearly see how enzymes perform. Thank you for watching!